and I'll go ahead and thank you. This thing's it's acting me WebEx in me went out my screen because I launched this a little bit differently. Hopefully it's all right. I'm going to move things around here so my screen looks a little bit different. And if you can just chat in, can you guys see my PowerPoint and hear me, everybody? Where are we at on this? All right, I got a yes, so we can go. All right, wonderful. So we're going into week 3. Program control is what it is. Had a little cold day today, so I know some people didn't get in that were finishing up their lab. You know, I don't know if you can get in there on set tomorrow. It's like even colder, so I don't know what LCC is doing, but let's see where we're at and try and stay ahead. So attendance, I'm got your attendance here. It logs it. Homework 2, I was grading a lot of homework 2s, and I saw that some other homework 2s went in, and I haven't graded them. There's just a couple of people outstanding with lab 2. You were going to get that to me. Some people wanted to take it home and just clean up all the paperwork and bring it to me. Next lab, that's fine. And so I always ask, you know, who is behind here? Well, you know, just because you don't have everything, you know, the lab graded and turned into me right now, you know, I'm really encouraging you to have that thing all done, ready to hand to me or ready to show me what you did with Sean Clausen or somebody else over the weekend. So we're ready to go because you don't want to get behind. All right. And then I just got that little note here. Once again, I really encourage you to read the lab before you get to class. You know, I don't want to yell at the people who kind of had it looked at it and did a good job preparing. That's what I encourage. This next one's kind of gnarly as far as scheduling programs. And so if you can read ahead, you know, and take what you read in the textbook and kind of apply it and kind of see what we're doing, you know, you'll be in a better place. Because what I do in the lab, sorry, this one coming up, is I kind of show you how to use, let's say, the MCR instruction set, and then boom, I drop this bomb on you. All right, well, now that you know how to do this and you fill these answers, do this part. And if you're just looking at it for the first time, you're going to get crushed. And so we'll review the options when we get to that lab, but prepare yourself. But we're going to start with our week 3 review. And we talked about, you know, safety relays. And they are part of an e-stop circuit. So when you think safety relays, you're going to think about dual channel e-stops. All right. It's not a stop circuit. That the stop circuit is what we learned in 131. You can have a combination of a stop and a start and an e-stop, most certainly. And that was part A. You kind of hook that up. And so just to reiterate, the safety relays don't, you know, they're trying to directly bring down the machine controller, all right? And they're hardwired to do that. We're not bringing down the machine controller using logic. We are killing the power to the machine controller. That's what the safety relay is going to do. It utilizes redundant contacts. We're going to do some redundancy tonight. You're going to be like, wow. The output switched on by the safety relay is often dual channel monitored. So a good example is dual safety contactors, and we were showing you that before, that you're going to come in here and you're going to turn on a safety contactor right here. Okay, and if you're going to turn on one safety contactor, why not turn on 2 that are in parallel, so that line 1 gets closed through 2 of them? That way, if something happens with these, you can turn them off, because the chances of 2 of them getting cooked, you know, is higher. And so when you look at a safety contactor, you still see line 1, line 2, line 3. These are for your power circuit, and these 3 contacts are not positively or force guided contacts. You know, this one can get burnt on, and this one could still open, and this one could still open. It's the red ones here. These red ones are going to be your monitoring contacts, and you know, these are the positively guided contacts that you're going to be using for this. And I'm assuming those that have worked have seen safety contactors like this. You guys, this is Allen Bradley. How about a yes or no? People have seen this kind of a safety contactor before? Pretty standard? Yeah, they're all over. Yep. So, you know, when we get to PLC 3, I've got trainers built up where I just have these already wired in parallel and then the monitoring contacts and the dual channel safety contacts and everything are the monitoring contacts are there. Okay. If you want to use them in these labs, you can. Okay. So safety relays. Can a relay contacts weld shut? Well, that's what we were talking about right here, is that, you can certainly get this welded shut so that when I let go of it, some of the contacts might be welded and they're just going to be stuck, while other ones would open, and that could be problematic or not. Okay, because it's just a basic contactor. But the safety contactor, the goal is that, if these are normally open and these are normally open, that if a single one of them get welded shut, then even though these other ones aren't welded shut, they don't open. Or if they're normally closed or normally open, they do not change the state. So that is the premise of how these things dual monitor each other. Okay, and so when you looked at the safety relay here, these were all the connections that we're learning about. But this is looking, I'll hang on a second. I don't know why I did that. I'm sharing again. Sorry, my screen just died. Are you guys back to see me, hear me, and seeing this PowerPoint? Yeah, weird. I don't know. Okay. It does that once in a while. So this relay right here, this dotted line right here indicates that there's a coil, the coil in there, I guess. And then this dotted line indicates that there's the coil in here. So this is one set of, positively guided contacts. It looks like an open and open and open and a closed. And then here's the other one that's an open and an open and then a closed. So these are in series. So I showed you that diagram last week that, the chance, getting this dual channel safety to self-monitor and one of these open, one of these closed and burn on and everything inside of here, that is your safety features of this. This normally closed contact right here, this is right here, this is not dual, there's not two contacts in series. And this one, there isn't two contacts in series either. And what these are for, these can be wired to your PLC for monitoring purposes, so the PLC can see what's going on or not. And so, you don't need a dual, you don't need redundant contacts and everything just to get a little signal to your PLC. You want these redundant contacts to try and kill your machine controller. Okay, so I'm going to really dig into this on this slide for a little bit, and this is what most of the lecture is about, but I'm going to kind of jump around a little bit, and I don't know what you got. I put some stuff in your I gave you one of these that you're going to need, I think, for your quiz. But in your handouts that I give you, I've given you these. We're going to do these later, not the ones with the safety gates. Is there an extra one in your lab, like a little worksheet here that we can work on, or do you have it from before? You guys seen anything like this that we can draw some stuff on? What do you got in your packet? Anything? People looking? You gave you a few, the two you handed out in class. Okay. Well, I gave you a couple in class. Let's just use one of them, because one of them you're going to want for the quiz then. Okay. So here we go. Basically, I'm going to start up here again, and I'm going to go, line 1 and line 2. And this one, this is showing that it's going to be powered by line 1, line 2. Ours are AC. That's what we did. And I'm going to show you a couple of different things that you can do. So remember that this is just contacts that are closing. So, the thing that they talked about here that we did last time is a master control relay. Okay. And you used the master control relay to source and sync your IO in the last class. So I guess we could go, I guess, where do I want to pass this through? It doesn't matter, where I pass it. For purposes of space, I'm going to pass it on the opposite side of the load. Maybe I shouldn't do that. I'll put it over here. So let's just use this first contact here. I'm going to run voltage, into the contact, and then coming out of this side, that's where I could do, my stop, and then I could do my start, and then I could do my, CRM, and I could hold it with a CRM, and then, then that would go, that would go to there. So that's kind of what we did on the opening part, to say that, hey, I can still got a start stop here. But the start stop is not going to work unless this safety relay is reset. And we're not even dealing with this over here yet to see how it's reset. We're just talking about passing voltage through here. So this was the first thing we did. Scale of 1 to 10. Does that make sense that this is providing the E stop and this is providing the stop? Okay. 10's got stops and E stops here, right? All right. And then what we learned in 260 was, you had an output module right here, and you had an input module right here. And, here's my line 1 again. So I just swing it up here, I guess. And in order for this output module to get sourced, well, we could have passed this through the CRM right here. So CRM. So our output module is not going to get any voltage unless my master control relay was on. And then same thing for my field devices. My field devices have to come back to voltage anyways, so none of my inputs would work anyways, right? And I got that out, but it could be in or out. So this CRM contact right here, when you think about it, it is the master control relay, but the only way to get the master control relay online is with the safety relay here. So this little CRM here is already, we've made it much more redundant. So sourcing of the output module here, everybody feel okay about this scale? Once again, scale of 1 to 10, using a stop and an E-stop. Okay, so that's one thing. Let me see what else we got here. We got this, a safety relay to source in sync. Okay, well, if you just wanted to skip the master control relay, which you're still going to have, you're not necessarily gonna, but it might not involve the safety relay. The master control relay might still exist, but it might not involve this. It may or may not, depend on how you want to do it. Let's say I had my output modules here. So let me take another voltage through, I guess, this one here. And to bring this online, what I could do is, if I had an output module here, I got another output module, by the way, output module, and that's my voltage. Okay. And then, out of here, I've got, I don't want to put a solenoid on it, and maybe a light or something, red light. Well, then those are coming back to my ground there. So that's what you were doing with the last part of that, is you were passing the voltage through the safety relay into the output module. Okay. And so even if the PLC did say, turn on this output number 1 and turn on this output number 2, the PLC will turn them on, but there won't be any voltage to the module because the safety relay will be down. That's what you did in the last part. So here's another option of using safety relay. How about, everybody feel good about this? Scale of 1 to 10 about sourcing the output module through the safety relay. Yeah. So Georges, you say 8. Before, you guys in 260, you ran the voltage, originally we just ran it off the black wire, but then after a while you were running it through a master control relay, the voltage into the output module. And now all I'm doing, if we had a different an output module, is I'm running the voltage through the safety relay to deliver voltage to the output module. All right, so that safety relay is really safe. And so if I kill the voltage to the output module, that output module is not going to work. This output module is different than this one. All right, so there's some options. What else I got here? The safety relay turning on a motor or turns on a holding circuit. We did that. How about, I'm going to say a motor, often done with dual contactors. Okay, often done with dual contactors. So if I come here again, I can do a single contactor, dual contactor. Let's say I had voltage running into this switch. Remember, this is just a switch. So if we're just doing a single contactor, it could just turn on, K1 directly. and then that K1 gets down there. So basically all you're saying is I'm hooking up, you know, this voltage right here to that. And so if the safety relay resets, then boom, the contactor comes on, and that is my, K1 turning on, my motor here like this, K1, K1, K1. So that's just a single contactor, okay? I've already used my things here, but if I wanted a second contactor, one of these other ones, I'd have to run, a contactor through there and get rid of all this stuff. And that would be my, I could do a dual contactor here, K2. So I got to turn on K2 and K1, and they just automatically come on, through there. All right. So that's another way that you could do it. Okay. Does this make sense? Just automatically turning on a contactor, scale of 1, reset this, boom, the contactor comes on and the motor runs. That seems like you're making sense to people. Got tens, okay. I said turning on a contactor or a safety contactor. Let's say we were doing this. I'm kind of mixing all of this together. It wouldn't necessarily all be like this. What if right here I ran off of out of the output module, I ran, a K1 here, and then I ran, on another output, I ran a K2 there, and obviously those jump down to there. So I could have the PLC could be turning on the contactors if the safety relay was allowing it to get voltage. Okay, so it could go like that, or you want to get crazy. Get rid of the simple module here. You could, it's either or, you wouldn't be mixing all these. You could put your safety contactors right here, K1, and K2. This output module is turning those on. And in order for these to come on, because we've got the CRM right here, you'd have to turn the CRM on to get this closed, and the safety relay would have to be reset so that would be closed. So that's incorporating a master control relay and a safety relay and safety contacts by killing the sourcing lead to your output module. Okay, how it does that? Does that make sense? Scale of 1 to 10. That's a way that you might set this up with an MCR and a safety relay. Just somehow you're trying to kill the voltage, to the items. Okay, good. So you kill the voltage here. Okay, great. Or you kill, kill the voltage here, to kill, wherever you're killing the voltage on the other side of that, then your device is going down. So hopefully that's what's making sense, of how this looks. It says wiring schemes may look different, but function is all the same. And there's and I gave you that document last week that you can download and take a look at, and take a look at it. And they might look a little bit different. Like pills might look different than Omron, that might look different than Allen Bradley. But if you just follow the wires and say, oh yeah, this is just turning this on and off. And there's a million ways that you can mix this up to get it to work like what you want it to, right? It says review 2 ways to start a motor. So that's where I said I was kind of jumping ahead a little bit. So the safety relay turns on the motor directly, versus closing a control circuit. And so that once again is, I was just talking about, I want to turn the motor on. So just turn the safety relay on, bang, it's on. Or I want the PLC to turn on the motor, and that's this one here. I'm turning on the contactor. Or I only want to turn that on if the MCR is on and the safety relay is on and the PLC turns it on. This is probably a lot of what you're going to see like that. Okay. Which is pretty redundant. But hey, that's what this is about, redundancy. Wiring schemes maybe look different, but once again, it's different. And so when I say motor start hand on this, I'm just kind of crash coursing, all this stuff together. Safety relay on a work cell. So a work cell is going to have a ton of inputs that can inputs. Now I'm switching from outputs to inputs, because now we're going to talk about the inputs is a lot of inputs that can be wired in series. Okay, and so our inputs you remember our safety inputs when I come here, that was my S11, S12 is channel 1. So these two right here are channel 1. And then S21 and S22 are my inputs for channel 2. And so what we did is we took a dual channel e-stop. And so coming out of here, I had a normally closed, and that is tied into the normally closed on the second channel right there. Okay. So scale of 1 to 10, does everybody feel good about what a dual channel e-stop is? And when you push the button, both channels open and they get wired, into one channel is S11 and the other one's S21. Okay. So then what you do is you start looking at machine safety here. And this is you can follow, if you want to download this PowerPoint and click that link, that's what this is. But these are my safety devices, safety door switches, safety limit switches, e-stops, safety light curtains, safety mats, laser scanners, emergency stops, enabling switches. So these are my devices here, and they can get wired in series. Okay. So if I come back here and let's say I've got, an e-stop, right here on the work cell, but on the other side of the work cell, I've got another e-stop. So I want to be able to stop it at either location. Well, it's a lot of wires because in series, but just run this wire all the way over to the next e-stop, and run this wire all the way over to the next e-stop. And then you've got two e-stops in series, okay? And then let's say you've got a gate, you got to close the gate in order for this to work, Well, a gate is going to have, believe it or not, that's what we're going to go over tonight, like this right here. This has positively guided contacts in it so that when I close the gate right here, okay, when I put the key in, the gate closes, not just one contact closes, two contacts close. Because why close one contact like we did in 131 and 260 when you can close two sets of contacts? So this gate right here, this safety gate, it can be a set of contacts that get wired. Once again, these work together, okay? And then it shows you right here. I don't know, this safety mat, two sets of contacts. This light curtain controller, two sets of contacts. Any one of these, you just keep wiring the two sets of contacts in series here. And then, you wrap it around to S12 here. So my concept of explaining that everything now has two sets of contacts, and you can just put them in series because if any one of them opens, and it's whether it's a single contact, they're possibly guided, so they both got to open at the same time, that it's going to go down. Just how do you feel on a scale of 1 to 10 about just putting all these safety contacts in series here, going into that relay? Feeling good about it? Okay. I mean, this can get really good, and it does get good. These safety contacts right here, how about having a safety relay part of the safety relay circuit? So not only could we have here, maybe we've got another safety relay, which is, 13 and 14, which would be 13 and 14 here, and 23 and 24 here. Shoot, you could put a safety relay in series with a safety relay in series with the e-stops and the gates and everything. And then what you do is you just bring it all back to here, right? And then if any of that opens, the safety relay goes down, at which point over here we showed somehow we're killing the voltage here. That's a big V, sorry. We're killing the voltage coming down here with whatever safety system that we've got set up there, okay? So hopefully that's making a little bit of sense to you. And there's some examples there. That's what that little document that I showed you was. This is good. It's here. This talks about these contacts. Welded contacts here. If you weren't sure what that is, this is made to open. But if one of these welds on a if it's not a positively guided, force guided contact, then one can be welded and shut and the other one can open. Well, we don't want that. We want all or nothing, all open or all closed. Here's the opening of a welding contact showing you that this one remains closed because it's welded, but this one opens, all right? So this just kind of goes through and it talks about door switches and safety limit switches. It looks like a limit switch, but it's got two sets of possibly guided contacts in it, okay? And it just goes through to talk about standards, different gate keys. You know, this is just all the kind of the terminology. Here's e-stops, here's light curtain controllers, 2 channels worth of e-stop. That's there for you to take a look at. All right, keeping going through the lab. Part A, forcing. It was just the little practice converting studio, you know, using studio. Everybody got through that pretty good. But I noticed that some people didn't read the lab ahead because the program was not scheduled. So you wrote it and then you were pushing the button and nothing was happening. And the reason nothing was happening, because it wasn't scheduled. So those that read ahead knew that they had to write the program and then they had to schedule it. So I hope you didn't waste too much time trying to figure out why this didn't work, because then on the next page it said you have to schedule this. Okay. So when you were pushing the start push button, you know, it was working start and stop, depending on if you had it scheduled or not. So scale of 1 to 10, does that make sense what I just said, that you need to schedule this subroutine in your main? Did everybody get that out of there? That you can write a subroutine, but if you don't schedule it, it's not going to run. Okay. That's what this week is about, is scheduling. This week is going to be your scheduling nightmare. You're going to be like, man, Sean, this is crazy. How do you come up with this? I'm like, I don't know, man. I look at this lab, I'm like, man, how did I come up with this? This was awesome. But you might not think so, but we did a lot of scheduling this week. And then the forcing we talked about, did the PLC program replace the safety relay? You know, because we programmed all that into there, and some people were like pushing the buttons to simulate how it works. Yeah, that's cool. It works, but it doesn't replace the safety relay, because as soon as what you were programming, it was fictional. So that little diagram that you programmed, there's not like a relay that's really opening or closing, like all those contacts, since they're opening and closing, they don't exist. Where when you have a safety relay, it's a real device that has all that redundant safety circuit hardwired into it, and the safety relay is safe. The program isn't safe at all. We talked about needing to enable forces. Instructions were in the lab. We went through and did some forcing, and that was different than pushing -1 into the output module. So I showed you guys that by pushing -1 into the output module, all the lights would come on. All the lights would come on if there wasn't something in the ladder logic telling them to turn it on. So if I were to come right here and I had PB2, and let's say this was OTL, no, OTE, let's do an OTE. If for some reason this was, you know, toggled on, or it was normally closed or something, or if it was, you know, toggled off, which is more likely the case, then when I put -1 in, all the lights would come in, except for, this would have to be like light 1, you know, whatever light this was, light 1. All the lights would come on, except this one, because the ladder logic, because this is false, is telling it to turn off. So by putting the -1 in, it's not really forcing. It's just a quick way. If you didn't have any other ladder logic, it's just a quick way to see if everything comes on, but the ladder logic will supersede the data table. So scale of 1 to 10, does that make sense? What I'm talking about there, just a quick way to go in and turn on, you know, put a 1 in the output module and see if it works. That's not forcing though. That is not forcing. If I came here and if this was false and this was off, but I came right here and I went and I enabled my forces, this would come on just like we did before, even though nobody was pushing the button. That's different. It is going to take the 1. It is going to put the 1 in the data into the data table. All right. Whereas if it wasn't forced, once again, and I put a 1 into a data table, it would instantly be written over as 0 because the run's not true. Hopefully that makes sense to you guys, and just, yeah, I can elaborate or show you on the PLC if you want. But getting into the data table is going to be the controller tags right here. Give me my controller tags. You're going to be getting into here to these a lot more because you're trying to figure out, crap, is my input working? And, when you're in, I'm not online, but, when you're monitoring tags here, you can start trying to see if there's ones here like there should be. And is it reading the input or the outputs, everything like it should be? And so in the controller tags here, especially on the outputs here, where you're going to be, taking a look at whether it's on or not in the data, you know, that's where it's at. And so once again, I know I say that once again a lot. So this is the word, the 32-bit word. We only have 16 outputs. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 14, 14, 15. It's only these outputs here because we only have 16 bits, right? And it's shown like you did in the slick. Whereas here's data 0, which is that one. Here's data 1, which is the second one. Here's data 3, which this is just showing the data table vertically versus horizontally. Scale of 1 to 10, after looking at some outputs, does this data table make sense? That it's similar to the Slick 500? Yeah, it's a lot more confusing. It's the only problem. It's like, man, but I like the Slick 500 because it's really easy to learn this kind of a data table here. But you'll really be getting into this because you can take a look at this as binary. You can look at it as decimal. You can look at these as these are going to be showing as binaries and decimals. So you'll get flying around it a lot. Clear fault. So clearing the fault is going to be found in the literature. You want to read on the stuff that I hand out because we're going to induce a fault in the controller. And then so you want to go in and clear that fault. And some people will really mess the controller up and you won't be able to clear the fault because you won't be able to go online because it's so messed up. And so there's some information in there about how to get in there and clear the fault after you mess it up. But that's pretty common. You'll fault the controller, especially the IO is wrong or something like that. And you need to clear it and then fix it. And then you can go back online. All right. Search. And so the search instructions, once again, are found in the literature. And, my little one right here that I'll be showing you later. This is the program for PLC 30 downstairs on the Flex, on that big machine downstairs with the Fanuc robots. And did we talk about this? Has everybody seen that before? The robot work cell downstairs. You guys seen the robot work cell? I got a yes there. Anybody else see what I'm talking about? All the robot in the main robot lab down there at LCC? Nobody. How about no's? Yes. Okay. Hopefully you guys see it. Yes. This is zone 30. This is one of the items here, and this is what we're going to be talking about scheduling. So this is the program for that. And if you were trying to find something like you wanted to come here and you needed to find, I needed something's going on with the e-stop, and then you can go that and you want to find all, and it will go through, and it's going down right here, and it's finding all the e-stops, and you're like, wow, this is really messed up. But this is a good example because there's a couple 100,000 lines of code, and if you're looking for something, you see it's pounding through all this trying to find, my references to e-stop, and then hopefully after this week, when you fully understand scheduling, you would be able to go in and find out, where this is. But this search mechanism, you see it's still searching through this program, trying to find, this tag right here. So let's give it another like 30 seconds to see if it will finalize finding all these things. All right, there it goes. So it found it. Now you're like, oh, which one is it? Well, it found 300. It found 626 occurrences of e-stop. So hopefully you've labeled things really well, because if you want to find those 626 things, they're all right here. Okay, and you're like, well, what's going on? Well, remember, you can just kind of click on this right here, and what it will do is it will take you to that part of the code about what's going on. Okay, so there's some problems. If you got an error, you click on the blue and it will take you there. So how did we do on that, by the way? When you were trying to download and you had an error and it told you had an error, were you able to click on the blue down here and it will take you right to your error, to what you got it fixed? Scale of 1 to 10. Did you see that yet? Okay, that's the way it works. Now remember, a warning is different than an error. It will download with a warning, and you're going to get warning downloads this time because I'm messing around with the lab. Error, it won't download. Click on this, it will take you to that. Okay. Online edit compile. So that was to double click the rung. And I think I showed everybody that if you wanted to change something when you're online in your main routine right here, I'm not online, you would double click the rung right here and it would create an edited rung. You could change it a little bit, and then you would click the green arrow. I'm not getting it up here because I'm not online or editing, and then boom, all of a sudden it updates it. Online editing, double click, change, green arrow, yes or no? Everybody good on this? The online editing. If not, you want to watch that video. Everybody good on it? Yeah, okay. Don't be a hog though. Just don't just take over the controller for 4 hours and do everything online edit. You still gotta be nice and share the controller. Okay, it's really fast. We talked about programming coils and then just change the instructions. JSR, OTE, TON, whatever. You can change accept all your rungs edits quickly. You can edit mobile rungs at once. That's the problem. Let's just talk about that. So when you get here and you're like, oh, this rung's wrong, and you double click it and it launches the alternate rung, and then you click here and you click here and click here, and then you got people that got like 7 rungs open that you've edited them all and you haven't compiled it yet, and then you click the green compile button and then it doesn't work, and you're like, wow, you just changed too much. I usually just change one thing at a time and then hit the green button and compile it and see if it works, or 2 maybe, but definitely not like 10 or 15 things at once and hit compile, because you don't know what happened. All right, so I can't wait for you to make that mistake. You're like, man, I don't know what I just did. Yeah, I don't know either. Timers and counters. So the timer and counter program, this is how long did it take to create that program. I think everybody kind of came up with it pretty quick, and then they scheduled it. They did a good job of scheduling it. You're pushing the light in it, and then it came on because the done bit was getting done. And so, I thought that we did good with the timers and counters. So, I guess scale of 1 to 10, do you feel good about timers and counters? Do I need to break down? So we mostly use the done bits on this. Do I really need to break this? Okay. We did have some questions about the overflow and the underflow and such. And so let me see if I got a local tag here. I didn't have one. I can come right here and make something called counter. And I'm going to come right here, and the data type is counter, and then data will be truncated. Okay. And so I made a little tag called counter, right? And so you just want to remember that the counter comes in with our done bits and everything, and those are Booleans. That is either done or it's not. In preset, or accumulation, when that comes in, that accumulation, it's coming in as a 32. It's coming in as 32 bits. So, the decimal here. Let's pick a number. 2 billion. Let me see if I got it. 2 billion 200 million. 1 2 3 1 2 3. I think that's 2 billion 200 million. And it takes. Be able to set it. Okay, I know. It should take it. Oh, why not? Give it to me. Oh, I was too long. Okay, so once again, what is that? If you want to look at a binary, it's this number, right here. If I want to change that number, these are the big ones over here. I could go 1 1, and then if I went back to decimal again, I made it, a bigger number. But when you exceed the maximum value of this, then you get the overflow. Okay, it's not. It's not like, hey, I set my counter to 10 and I hit 11. Well, no, that's the done bit. And, it'll keep counting 12, 13, 14, 15. It'll be done, really done. I'm really done. It'll keep counting. It's when you exceed the value of a dent, which is 2.2 billion or something like that. Okay. Or go under negative 2.2 billion. And then I said that an int is, 1111111. The biggest thing would be 32,767. So at 32,768, you get an overflow. So as I explain that to you guys, that these numbers, and I'll give you one more. Sorry, before I ask the question. An int or a SINT is 8 bits. So it's you go 1 1 1 1 1 1 1 1 1 1 1 1. It's 127. All right, and if you exceed that, you would get an overflow. So as I explain that real quick, scale of 1 to 10, does that make a little bit of sense that there's different values for different data types. Dense being pretty big. Dense gives you a lot of data. All right. We will get into this in a couple of weeks, really into it. I hope that makes sense to you guys. All right. I was trying to explain it to you guys. All right. Intake tie down. There's 2 timers versus 1. Yeah, Michael, that's okay. We'll get into it. As you read through the book, there'll be a lot of references to data types. That's why I just wanted to be sure that you're kind of understanding that dent's 32 bits and versus int is 16 bits, booleans 0 or 1. Just be aware of that. More bits, bigger number. Yeah, more bit good. So 2 timers versus 1. Reset the light was a problem. This was like a little anti-tie down. Looks like with 1 timer here. There's a little video there if you wanted to watch the counter reset problem, because it looks like when I push the buttons here, input 1 and input 2, I was input 1 or 2, I was getting the timer to be done, which was counting. But the issue was, as soon as I let go of one of the buttons, the timer was still done, and so my anti-tie down reset. Even though I was reset, my timer done hung on for the rest of the scan, which was only a few milliseconds. So everything was reset, ready to go again. But this didn't get reset for a couple milliseconds, and then it got a 1 on there. So you could do it with a one shot, or what you could, some people did some mapping of the I/O and stuff like that to get it to work right. But there's a little video there if you wanted to take a look at what the anti-tie down issues might be. We did the 2-hand safety relay, and it's way safer than the programmed anti-tie down, because once again, the program anti-tie down with all these timers and lights and contacts, it's all fictional. There's nothing going to burn on here because there's no current going through any of this. Versus when you have the 2-hand relay, which we use, it actually has to close right here. This actually has to come on. And when it comes on, 13 and 14, 23 and 24, 23 and 20, these things close. And they're multiple sets of contacts. They're all self-monitoring each other with all that circuitry and everything like that. So this is really closing, okay? And so we were passing the circuit through here. So just to reiterate one more time, what did we do? Oh yeah, here we go. We did this. We used, it wasn't a CRM, but it was like we killed, oh, here it was. Yeah, we killed the voltage out of the output module. And then that was going to the lights that we were blinking, okay? So you're like, well, this says MSR 131, and this says STI. Well, yeah, it's different. This is not this, but I'm just using the 13s and 14s and everything. But this is what we did for the last part, is we passed the voltage here. So even though the PLC was blink, might want to blink this light off and on, off and off, on and off, the actual contacts of this also have to be closed, okay? So that, we killed the PLC with a signal, by the way, because I'm talking fast, I know. We took these contacts here and we, ran voltage here, and we ran this into the input module as I1. So when this was closed, I1 was closed, and that was the start of our PLC ladder logic to do a cascading timer, okay? That's what we did there. So this concept here, that's what we did on the last one. I know most people got it done pretty well, but just to recheck, yes or no, or 10, 8, the way that 2-hand safety relay worked. Yeah, we got through it. So I'm guessing that most people did pretty well on it. You know what I mean? And I did want to touch, and I talked to a student about cascading timers counters, because we do a lot of cascading. So whenever you cascade the timer counters, use the maintained contact, whether it's latched or memory or a contact through a safety relay, whatever's maintained. Use that to turn on to turn the light on. Don't turn on the timer, turn on the light, okay? So this would be, I guess this could be the safety relay, okay? Turn on the light. And then that same contact then turns on timer 1, which is the blink timer, okay? And have the blink timer blink the light, okay? T1 done. Have that blink the light off, okay? Keep the light on its own run, and don't use any timer timing bits or ENs and trying to, jack up this ladder logic program that should be as simple as possible, but no simpler. So this was T1, have that, T1 done. It did the blink, and it does the T2, and that's the reset, okay? And then when the reset gets done, T2 done opens up, and because they're not, I did not use retentive, reset, and a blink. So this is about the simplest way that I can use with a blink timer and a reset timer like this, keeping the actual field device on its own run. Don't get it trapped. All right. Scale of 1 to 10. You like my blinking light circuit there, cascading timer counter? Yeah. Okay. We did a lot of this. Hopefully it really came through to you. The other thing that I want to add is that when you're counting the cycles, it needs to be the end of the cycle, not the beginning of the cycle. So this goes all the way. This instantly comes on, because that's what we got with you guys. Like you hit the 2-hand channel here, and then 2 seconds later the light came on because you were turning on the timer. No, when you hit the safety relay, the light should come on right away. And then 2 seconds later, it should go off. It shouldn't come on after 2 seconds. So that's why you do this. And same thing when you're counting, this is the last thing to occur. So use the T2 done as your counter, C1, to advance your counter, okay? Don't use the light to advance your counter. Don't use T1 to advance your counter. Use the completion of the process. You turn the light on, it was all the way on, then it was off, and it was all the way off. And at that point, count the process. Okay. Hopefully that's making sense to you too. You'll get in trouble with some of the labs. All right. Machine control MCR safety relay is the MCR. This is. I'm not going to go much more into this. This is the diagram. Have you guys seen this diagram like 8 times last semester? Did you guys look at this diagram like 8 times last semester or what? Yes. How about the rest of you? Ever seen anybody? How about anybody not ever seen this before? I mean, this was all over 260, right? Okay. And that's what this is showing right here is a CRM, a master control relay that turned on the IO modules. Don't say that, man. This was in the PowerPoints, handouts, quizzes, capstone. All right, I know. But this was the power circuit, the transformer. We don't have a transformer. X1 and X2 is our black and white. We hooked up a CRM so that we had to turn the CRM on right here in order to feed the IO modules, the sourcing, the syncing, the field devices. They were not going to work unless the CRM was on. So that was what I showed you before with the safety relay. Instead of having multiple e-stop switches here, which is not an e-stop, it's a stop, we basically replaced these multiple e-stop switches here, possibly with a safety relay contact. It just happens to be activated by a safety relay that has multiple e-stops, okay? So we just took this to the next level of using a safety relay as compared to a master control relay. But you could do both. You could put a stop here and a close contact for the safety relay. And I showed you that too. And this is what we just did: safety relay to source outputs or safety relay to control the outputs. And so the thing that I wanted to talk about right here once again is if you have an output module right here, here's your output module. Here's my voltage, my source for it. If I put the safety relay contact right here, which is 13 and 14, well then every output coming off of here is going to die when the safety relay goes down. Okay, that's what I did. Now, what if you don't really want everyone to come down. Maybe you just want one of the controllers to come down, okay? At that point, maybe you just leave this the way that it used to be, where the CRM, which was, 1 and 2, I think, it was 1 and 2 on this relay, 1 and 2, that gives voltage to this. Maybe it's just the first output that's really dangerous. Maybe it's just this device right here that we want to put the 13 and the 14 on to bring this down, but then these other outputs here, whether they're solenoids or lights or whatever, they will still work. So if I hit the CRM, or if I hit the E-stop on the safety relay, this goes down, but all the rest of the outputs still work. So 2 options: put the safety relay here and just kill everything, or put the safety relay on the individual device that you want to bring down. Scale of 1 to 10, do you understand that? You could do all or 1, or all or 2, maybe, I don't know, something like that. That's making sense to you? You're saying 10s. Hopefully you're feeling good about this. It's just a relay that's closing. All right. Use safety relay for a PLC input. Yeah, we did that. And you did that, with this one right here. You took, one of these contacts here, which should took 41 and 42, because those are the monitoring contacts here. 41 and 42 are your monitoring contacts, 51 and 52, and wire those monitoring contacts back into the PLC to kill your program. Because the safety relay is going to bring down it is going to directly bring down the field device because it's hardwired. But we should probably kill the program while we're at it, just so the program's still not trying to blink something or kill somebody. And so what you'll want to do on that is you learned, on your system bits, you had you would have some type of a stop that's normally closed, and you would have some kind of a start, and then you would have some type of a bit that was your system bit, and then that would be here, my system bit. Okay. And so, you just start stop. Then your system bit was kind of like your lowest form of state manager, where that enabled all these rungs. If this wasn't on, none of these rungs were going to work, right? And then we did a lot with monitoring of a motor starter, where you put the overloads right here, right? So you put the overloads here, and those are normally closed. So hey, if you kill the overloads, boom, the system goes down, everything farther down goes down. Okay. So real quickly, does this make sense here, right? This is what you guys learned in 260, that the overload brings down the system bit, and the system bit kills, it's going to reset everything, kill everything, and then you fix the overload, you fix the motor, reset the overload, and then try and start again. Okay. So yeah, this system bit right here, the stop button does it. Shoot, put put the safety relay in here if you want. As far as the PLC is going, if you're going to monitor it, and you want the system bit on, run the contact through the monitoring, and that's 41 and 42, right? 41 and 42, so that if the safety relay goes down, or the stop, or whatever, the system bit goes down, everything goes down. So that's just another way that you would run the safety relay to kill the system, most likely, if it went down. And you don't want to use your 13 and 14, 23 and 24, 33 and 34, because those are your good contacts. Those are the ones that you want to bring down current coming through there. 41 and 42 are just monitoring. There's nothing special about them. They're just like a normal relay contact. So have that bring down the system. Okay, doing good. My stamp solution, and I'll give you guys a little bit of a break here in a little bit after we do the quiz review. So we got this hooked up. Remember, this was switch 1, so people had to follow the wires X1 through a couple of switches to X2 and then S13 else and the switches, and then boom, you were getting the safety relay to reset. And so at that point, you were taking once again 41 and 42, because when I pushed the buttons, that came true. 41 and 42 was my blinking circuit that kept it blinking. If I let go, it quit blinking because it was basically on or off. So that blinking circuit. And then I ran the lights that were blinking everything through the safety contacts, 13, 14, 23, 24, so that it was doubly redundant. This was actually bringing down the light, no way for that light to be on. And then the other one was triggering my PLC program to blink a light. And I think we did good. We did good on that. Homework review. This was the two-hand control, which was class C or type 3, depending on how you read the literature. And it was just going back to that information that I had put in your packet and online to go through and read it and do a risk assessment. And basically, two-hand control is dealing with stamping stations. And I just wanted to go through and explain your answer. And so finally, before we take a little break here, was the quiz review. The quizzes were okay, I think. A base tag defines memory location where the data is stored. The alias is the name, like a conveyor 1 or light 2 or solenoid, the stamp solenoid or whatever, but it's a base tag. The memory organization uses flexible memory structure with no errors allocated for specific data types. There's no T3, there's no B3, T4, C5s. As soon as you create it, it's created. Okay. Control logics use tags to refer to memory locations. That's going to be the alias for the base data. The physical address for high limit it's 012. It's on the local rack, on the PLC, so it's local 2. It's an output, and it's on bit 5 right here. There's an output module. Okay, output 2 data 5. We did pretty good on this right here. This was good. The window shown of creating it. Oh, the next one. This was the new tag window. We did that using the new tag window. This was pretty good. That the student's trying to do something here with a push button, but one thing is there's no I/O down here. A lot of people got that. There's no input or output module, and you're not creating. You're not going to be able to find the data if you don't first of all install your input and your output modules. And then you're trying to get some wrong data type here. It's a DINT. Well, a push button is a Boolean. So there was a couple of issues there. The type of data is predefined. You bring in a counter and everything's, predefined for you, right? A module defined would be if you bring in install an input module and output module. It'll create your controller tags for you. Tags are created by any of these tag editor by entering names using question marks. Yep. The window is an example of the monitoring tag window. We're doing that, and the control logic use asynchronous I/O and logic scans, which will be next week when we get into that. Okay, so that was the quiz. They were pretty good. All right, doing well. We're really going to get into, let me see what we got here, into program control. Okay, and before we get into this, I'm going to give everybody like 5 minutes just to get up and stretch and run around. And I'll be back at 7:12 to do some more of this. Okay, so take 5 minutes. Let me go get some water. We've got 2 minutes. We're doing good. Let's see, have this activity. Okay, we're gonna go here again. Need a really sharp pencil for this because this is a lot. All right. So, are you with me? Everybody ready to go again on this next thing? Program control. Can you hear me? See me? Ready to go? Yes, I'm getting yeses. Let's do it. All right, we're gonna crank it. All right. So, we're gonna do the program control, which is MCR, jump, label, sub routines, returns, no ops, stuff like that. So the once again, you're gonna want it straight out of the books. You want to take a good hard look at it and read the lab. Couple of things. When I do the lab, I'm kind of have you tinker around with a little bit of scheduling, just for fun. And so what we have going in our main routine, for example, right here is, you know, I have the selector switch, and so I cycle through like the different parts of the lab. So I got selector switch 1, and if this was true and true, then I would run part A. But if this one was on, that would be off. And if this one was on, that'd be off and off. So I was kind of using selector switches to kind of jump around to the different parts of the lab. And so when you were doing your subroutines, you would come over here and you could do this and just do JSR and create a subroutine. And that's where you had those input parameters that I said come in here. And this is in the way. Sorry, I got a little problem here. My screen's in the way. All right, if I came here and I went remove instruction parameter, that's what you did. And I don't have any routines created, but this would be part B. And then I could jump around like that. Now, part A and B, that would be over here. I did my main program and I would add a new routine, which would be like, that would be part A. And I could program it in ladder. I could program it in different languages, but I don't know why you'd want to program in structure, text, function, block, or sequential, because you only know ladder logic right now. But it would create that routine, and that's what that's scheduling. And inside of here would be, all of your ladder logic. Okay, so this is just fancy to just kind of use the selector switches to do it. If you get going and there's too much going on in your lab and you just want to kill your subs because I don't want you to use an output more than once. You kind of could with this, but you'll be a little bit confused. So just manage your IO, get a good IO legend and a good IO map so you know what's going on. But the other instruction that I was showing people was right here. If you don't want this to go, you can just come right here and do AFI, right? And that's an always false instruction. And so what that does is it'll just kill that subroutine so that anything that was going on in there will be gone. And then if you need if you're working on something and you'll see that you need something here on the right, on the output side, okay? And so you put an output here and you just need like a dead rung, that is going to be called an NOP, a no-op, okay? A no operation, if you need the rung there. But AFI to kind of fill the rung if you need it, all right? A couple other things you're going to learn. If this JSR was running and there was something on in here, and I threw an AFI here, or if I unscheduled it by hitting the selector switches, you're going to find that there's retentive nature of these items. That just because you unscheduled an output, that doesn't mean that the light goes off in it. That means it's no longer scanned. And a lot of times you're going to find that even though it's not an OTL, that the light just stays on because you never turned it off before you unscheduled it, okay? So that is a big part of the lab to work through and see what's going on, you know, with those things. So those are the things that we're doing. And like I said, I was kind of using a little bit of selector switch scheduling. Your lab will get kind of messy. All right, so before we get into that too much, because a lot of that's through the book, I want to go over some of the safety switches. Now, this is safety switch activity 1, safety switch activity 2. I actually didn't print that off, but I did print off some safety switch stuff to, you know, go over and be sure you understand, okay? And so what I'm going to do is I'm going to start with looking at the safety switch right here, okay? And so the safety switch is going to be labeled 21, 21, 22, and this, I think I got some other contacts, 5 and 3, and then I've got some other contacts here. I don't think I've got these labeled yet, but you're going to take your multimeter of this and start trying to figure out what's going on based on your diagram here that's showing 11, 12, 21, 22, you know, and then here's some more 21s and 22s. These are showing the contacts related to the safety switch. And this is also in your, on the D2L, if you want to download it, and I think it's in your packet, okay? And so it works like this. Like, let's say 21 and 22 are here and here, and they might be normally open. And so if I had my multimeter here, nothing would be going on. But when I put my gate in here and close it, beep, it starts beeping. So it's just a switch that's closing, okay? And, you know, if we can close one switch, why not close 2 switches that are possibly guided, that the switches are all or nothing, that they have to be all closed or all open, okay? So that's some of the switches on here, and that's showing that when this key is in, 11 and 12 are going to be closed, and 21 and 22 are going to be closed. And this little dotted line is kind of indicating that, yeah, the key went in, these closed, these other ones open, etc. Okay, so far so good. Yes, that makes sense. They're going to show some contacts here for the key, and that you'll be able to like fluke that key out a little bit. You'll be able to fluke this out a little bit and find out what's beeping, what's not when you pull this key in and out. I hope so. Okay. The other thing that gets people a little bit messed up is that you can lock this, okay? And so this right here is a solenoid, and you can see all these contacts open and close when I turn this on, and it's, in this case, you know, 3 and 4, and I've got this is 3 and negative voltage. So I'm guessing if I bring negative voltage here and 3 here, that this will lock, okay? And you'll hear it go click. And when it clicks and it locks, you cannot take the key out because a little solenoid comes in and it pushes in place and it locks it, and you can't take it out. It's locked, okay? And so that's like you shut a door and you click a toggle switch and then you lock it, all right? And so by the way, that might look something like this, where you might have on this input, you know, you could have a toggle switch wired in, and then when you click it, you could write a program that would deliver, you know, voltage here, right? And then boom, you would hear it click. Okay. 0 speed switch. Yeah, you can do there's different stuff. Yeah. 0 speed switch could lock it or unlock it. Yeah, there's a lot of things you want. So I imagine you imagine what this looks. This turns on this. So click this, boom, that comes on, and you'll hear it lock. Well, when it locks, guess what? These contacts close and these ones open. And so there's redundant contacts in here. that are forced together. So you could monitor these contacts, and you could monitor these contacts. So you could run some of these contacts, or one set of these contacts, into the input module, and then the PLC would know if it's shut or not. You could run one of these contacts into the input module, and then it would know it was locked or not, because when these closes, you get a signal. When you put the key in, you get a signal. So we could certainly monitor whether it's locked or whether it's closed. Scale of 1 to 10, do you agree with that? That you could wire these inputs into the input module, the input module over here, and monitor the status of the switch? Yeah, why not? So this has a variety of inputs and outputs. It's got this green and red light. I don't know. I might have some of this hooked up. You could mess with it a little bit and see what's going on, but I don't know if I really need that green and red light. You can turn on a green or red light on the controller. But it's the safety contacts here that are going to be interesting to us. Okay, so if I'm coming right here and I'm going, and I know yours is a little bit smaller than mine, but hopefully you can get this drawn. You know, I need some e-stops here, and they can be in series. So if I wanted to have an e-stop, let's throw an e-stop in here, because it's always good to have, you know, an e-stop in there. There's an e-stop in that channel. There's an e-stop in that channel. Okay. And then what I might want to do is I might say, okay, well, the e-stop can't be pressed and the door has to be shut. How about that? So what this is, I'm going to draw arrows here because it's too much. This is going to go up to 12, right? And this 12 right here is going down to S11. That makes sense. So I just don't have to run a bunch of wires there. Everybody understand how I'm doing this? Feel good about it? Okay. Wonderful. And then this one right here, S21, that's another one. Well, these work together. So this is 22. So this is going to 22. And then this is going to S21. Okay. So now I've got two safety devices that are wired in series. That the e-stop has to be reset and the door has to be shut. And then boom, my safety relay will come online if it's reset. Oh, you want to put a reset on it? That's fine. Reset's right here. There's my push button. There's my reset right there on my safety relay. So pull the e-stop, shut the door, hit reset, and then boom, 13 and 14 close. All right. And so that's what we were talking about. Like, what are you going to do with 13 and 14? Well, how about this? What if I took the voltage here and I just wrapped it around to there? So I got voltage running to my module. So boom, reset it, and then my output module's got voltage. Yay! And now I can turn on outputs. All right. And then anyways, this S12 is the line, and it's going up here to 11. And this is going to S12 because we need to wrap it through there and come back. And this goes up to 20. This is 21, and then this is going back to S22. So there you go. There you've got two sets of contacts on the safety gate and contacts on the safety relay working like this. So far, scale 1 to 10, feel good about everything that I do around this? You like it? Okay. Now, I mean, you can go crazy on this. Like, what do you want to do with your monitoring? See this right here? These are my monitoring, right? Where before we were putting, you know, closed contacts here to see that, you know, stuff had to be closed. I mean, there's these contacts. Instead of doing it this way, we could be monitoring the door. We could be monitoring whether it's locked or not. You know, something could be going on, or if we were turning on motor starters and contactors. That could be the contactors, the safety contactors, right here that we could be running the normally closed contacts right here into there to be sure that that safety contactor is off like it's supposed to be. So, there's just a lot of craziness that you can do here. Let me see what else. The inputs. Do I want to know that this is shut? So I could take my 41 and 42 right here. Let's say that was it. And so it's a little bit dicey, but all right, how about this? I'm going to go like this, and I'm going to go I1. And then I1 right here is what is coming over to 42. That's, boom, I know that the door is shut. Because remember, there's two things. There's the PLC needs to know if the door is shut or not to do all the stuff that's fictional. And then there's a safety relay that needs to know if the door is shut so that it can absolutely kill every output device. And they're separate. One's hardwired and one's programmed. Same thing. You want to be sure that this thing's locked. And so you got 41 and 42 right here as well. So this 42 right here could go to I2. And this right here could go to that 42. So hey, if for some reason I hit the selector switch here and I turned on the output, this will lock. And then this will monitor to say, hey, somebody locked the door. The PLC will know in the program that somebody locked the door. Okay. The safety relay won't know that, but the PLC program will. Okay, because that's separate. Everybody concur with that the PLC, you could wire this and the PLC will know that it's shut, but the safety relay at this point doesn't know that it's shut. Okay. So, if you go to the next one, and I'm not going to, I could get really crazy here. I don't know. You want to lock it? How about this? We still got this right here running to S11 like we did a minute ago that was in series with an E-stop. Well, shoot. Why don't we run that through 13 and 14? This running through 13 or through 14 right there. And then before we ran this back to S12, and now run this back to S12. S12, yep. Okay. And same thing for this one. Before this ran to, S21. This one here before ran to S21. Okay. And then take this out of here. It's going to be a little messy. 33 and 34. So run this into there. And now run this back to S22. Okay. We're like, all right, what do we just do? Well, I'm going to draw one item, not two, but there's two of each of these contacts. If we still had, an E-stop right here, right? Running up then to S11. Basically what we did is we ran the E-stop through the contacts of the key to be sure it's shut, or to be sure it's shut, run through the contacts of whether it was locked or not, locked, and then we ran it back to S12. So that's what that is. S11 ran through this circuit that was daisy chained together, coming back to S12 like that. So in order to shut this, you have to shut the door. You have to lock it. Remember, we were locking it by turning on 3 right here. And then we would have closed, closed, closed. And then if you wanted to reset here, right? If you wanted to reset this, bang, you're in business. No, you want to just say, shutting the door is an automatic reset, or locking the door, once it's shut and locked, an automatic reset. You could jumper that like that. And then you won't need to push the button to reset it. As soon as you shut the door and lock it, it will reset. Or if you wanted to, I don't know, you probably want a manual reset a lot of times on a safety relay. And we can still leave this as a manual reset. It's, you know, it's up to you. I don't know, push the manual reset. So, hey, shut the door, lock it, boom, boom, boom. There you go, right? And then, you know, we're still turning this on. And then we still have the monitoring contacts, 41 and 40, 41 and 42 and 41 and 42. Probably going back into the input so the PLC knows. But hey, man, you could do something down here with your monitoring contacts here, right? If you wanted to know that things are, that the doors, you know, if this is 41 and 42 and 41 and 42, then you have to shut the door, you have to lock the door with the selector switch like we did here. And then you have, you know, then this has to know that they're shut, and then you hit the reset and it resets. How about that? That pretty redundant for you? I mean, I can just go on all day with this about putting contacts within redundancy onto contacts, being more redundant, and then taking this and wiring it into the PLC input so it knows, oh yeah, wait, we forgot this. This, even on this one, this 41 right here, this has to go to I3, right? And then this goes to, you know, the 41 there. So now the PLC knows that safety relay is reset, this is reset, this is reset. And then so by that point, you know, what's your logic looking like for your system bit? Your system bit has now got, you know, all these contacts here that are, you know, locked, closed, you know, reset, you know, all these contacts can be used to turn on, you know, for your system bit, so that, you know, there's no scheduling going to happen on your thing unless everything's closed and locked as it should be. So, I mean, I can make this, they can make these up all day about how to do the redundancy. So scale of 1 to 10, you kind of getting the gist that I can use these contacts however I want to just create a lot of redundancy. Okay. The thing just to remember, the 13 to 14, the 23 to 24, here they are, the 23, the 33, 34s, 23, 20, same thing, 33, 34s. These contacts are the good ones. They're the good ones that pass current that you want to use to possibly bring down the circuit, or put them in series with your safety relay to bring that down. Okay, so you know these are going to come into here, and it's these here that's bringing your unit down. Whereas the 41s, 42s, 41s, 42s, a lot of those are just your monitoring. They're not as nice of contacts, and they can kind of go into here. Okay, and it would be the same if it was a safety light, a safety curtain controller, or anything like that. All right. So that is a switch activity 1 and 2. I didn't do that. I was just throwing some stuff in there randomly that it would maybe help you with that. Okay. Program control. These are the jump labels and everything. I'm going to kind of blow right through this because this will be the end. This is what you read in the book. It is fully laid out in the book. I don't think I can do a better job of explaining the way that the book did if you read it and looked at these nice pictures that they had. Okay, I'm just going to give you the cliff notes on this, and I really want you to understand it and read the lab and understand how you want to use these to do a little scheduling magic. Okay, higher master controllers are used. So this was the master control hardwired system that we just talked about. This doesn't have any safety relays on it. It's just old school start, stop, master control relay. And if the master control relay was on, well, then everything down here works. But if you hit stop, nothing down here works, okay? So the master control reset program or instruction set, it meant to mimic a hardwired circuit logically or fictionally, okay? And that was, you created a fence, right? That the MCR, whether this was on or off, the MCR here and the MCR here, then this zone was hot or not, almost like if somebody hit a master control relay on or a master control relay off. So that all that does is control all the logic inside of here, okay? And so the lab that you're going to do is you're going to mess with this. You know, turn it on, turn these things on, some latched, some not latched, some memory, not memory, and then turn it back off, and see which one of these retains memory, And then when you flick it back on, do they automatically come back on, or do they not? And when you do this, think about the way that it would work if it was hardwired electrically. It is set up to work just like this if it was hardwired electrically as programmed. All right. I mean, take a look. Like I said, it's in the book. You're going to do it in the lab. Now, one little disclaimer here: you do not want to ever use the master control MCR instruction set. We're going to do it in the lab just for fun here, but just for scheduling purpose and just for you to understand retentive nature of scheduling. But I don't think you should ever use the MCR because it's dangerous. Because when this is true, this is true. And if you have like multiple zones of MCRs and MCRs, and you got these pairs of MCRs throughout your program, and then in some, you might miss which one is what is the fence that you set up. You might miss a fence, and you can't figure out what's going on. It could be really dangerous. So we're going to do it just for fun. But you'll see, like, hey, this is a retentive timer or a non-retentive. If I kill this, does the retimer reset or does it not reset? So MCR, it's right out of the book. Got a little activity, and then I got a really hard activity to show you some other stuff. Jump instruction. You can do the jump instruction. I don't use the jump instruction that much. It could possibly save some scanning time, but here's a jump instruction so that if I hit the switch, it jumps over this ladder logic. Book fully explained it. It's going to jump to the label, and then this will not be executed anymore. So it's a way of scheduling some stuff that you want to run or don't want to run, and then you hit the switch back, and then it no longer jumps, and it will run everything between the jump and the label. But if you click it, it will just jump over everything like that. Like I said, I'm not scale 1 to 10. I don't know. It's out of the book. I hope it makes the reading make sense. And yeah, I mean, I don't know how to say it any better than what the book did. That's why I'm not going all into it. Here's your jump rungs. You want to be careful here because let me see this. Here's a jump. Here's a label. Let's only have one jump. Same thing. If you have multiple jumps in here, you could get a little confusing. You jump into this label or what label, but the lab just walks you through it. And so if you click this, it will jump over this. The solenoid 1, solenoid 2, and the pilot light would get jumped over. But what if these were on? What if they, if I jump over them, do they go off automatically? Or if they were OTLs latching, would they go off, or would they stay on when I jumped, and when I went back, what would happen? And that's what you're looking at, right here. Here's an OT, here's a latch. So when an MCR is almost like a jump. It's either making this zone hot and true, or it's making this zone not hot. So how does that work electrically versus mechanically? And they're different. Yeah, well, you'll see, follow instructions very carefully when you're going through and writing these little programs, because I'm going to have you like write this little jump program. Not a pre-selection option. It's in there. You can do jump. You want to do a JMP. Right here, you can just go JMP, and you can make a jump instruction if you want. So it's an instruction set that you may or may not use for scheduling. Okay, and that's what I'm saying is, when you make your little program, their little simple program, study it, study how it works. And because it only takes you a few minutes to write this and test and study it, and then I say, oh, now that you know how to do it, boom, do this, and everybody's like, oh, I don't know how to do it, right? Jump is there. It's here in your instructions right here. If you could do your program control instructions, there's JMP. Is that what you're asking for right there? Is where to find it? Yeah, it's all up there. Yep. They're going to be in there. Yeah. So Kate's asking about scanning and what, and are you going to time out? Is your watchdog timer going to time out and have an issue? It could be an issue, but one reason why some of these scheduling mechanisms aren't used as much is because the controllers are pretty powerful, and they'll get through that scan pretty fast. But you can get bogged down. But jump can save some scan time. So it's kind of a loaded question there. Yep. Nested subroutine. So if you're in this program, you can jump into this subroutine and be running code, and then this subroutine can call another subroutine and call another subroutine. But then when you get done, you have to go back to this subroutine and close it and close it and close it like this. So you can have call subs within subs. And so if you were, same with jump, if you were going to jump here and you're in a routine and you try and jump into a different subroutine, you're going to have problems. All right. So these are some scheduling things you get around and or get in trouble with. And this is what I talked about, the matrix, about calling subroutines. My big one is here, like the Inception. You guys have seen Inception with Leonardo DiCaprio, right? Everybody seen Inception? How about that? Yeah. How about yes or no on that movie, Inception? Or you guys got some movies to watch this weekend? Nobody's watching Inception. What? Movie's great, man. You guys gotta stay in the house. Let's see, get out of the house. You gotta stay in the house. So in Inception, it's about these espionage where they put you to sleep and then they're able to get into your dream, okay? And then to really manipulate people while they're dreaming, they get into that dream. So they're dreaming while they're dreaming and they're manipulating them. But in order to, at the very, when you're all done with your espionage, you have to wake up from the dream within a dream, then wake up from that dream in this dream, and then it all get all the way back to reality, okay? And that's what this nested subroutines do is if you're in a subroutine, you have to end it and then get back to the main program. Do not try and jump. Yeah, the matrix, no, yeah, do not try and jump it. The subroutine parameters, this is a really hard one of moving parameters into a subroutine, and you process the subroutine, and then you kick out the result, okay? This is going to be a hard part of the lab. I think you should read that. And then the fault subroutine, that's what I'm going to do. I'm having you do a jump and go to a fault routine to kind of go through, just to kind of see what faults look like when that happens. Now, the moral of the story is that on a modern PLC program that you might be troubleshooting, especially if you're a big company and they hired the stuff out, system integrator, but you got to fix it. You are going to have a hard time sometimes finding out what is going on because it's super complicated. So if I look at this program right here, here's my main task. This main system right here, that is not a subroutine. That's just continued organization within the main task. And remember, this is all continuous. So it runs this main task and it's going to come into here, and then it's going to run this main that probably is calling these subroutines here. It'll read all that ladder logic left to right, up and down. Then it will go to main zone, and then it will run the logic here in main zone. And in main zone has all these subroutines. And if I go into the main right here, let's just take a look at this main zone, go into the main, you can see that there's some scheduling going on here. Once we get here, here's an unconditionally scheduled subroutine. It's going to run the map inputs. And then this is always off. It's going to run these subroutines and then these subroutines. And then it's just going to, here's startup. This is automatically going to run when it comes into here. When it gets to it, this is automatically going to run. This is automatically run. These are unconditionally scheduled. And it's going to go through all these subs, however it calls. And then it will run this one, this one, this one, this one, this one, this one. Excuse me. It'll run all this ladder logic like it's reading a book, left to right, chapter by chapter. And then it will come back up to here again, and it will start right here again and do it. And it will do it all really fast, all right? Excuse me. Yikes. All right. So when you get into this, it's gonna be like, man, what is going on? So where am I at? I'm in right here in the main. So I'm in the main. I don't know what this is doing. This is unconditionally scheduled. It's going to run some PLC running. So this is just going to keep track of how long my PLC has been running. Okay. And then this is SFS that happens on the first scan. So on the first scan, one scan, on the first time when you go into run mode, it runs this stuff right here. And then this right here, it'll map the inputs unconditionally. There's no condition here. This subroutine, this panel test, is conditional. If this is on or off, it's going to call this sub or not call this sub. And that's what I was kind of screwing around with right here when I talked about having these selector switches call or not call a sub. You'll have a little bit of conditional scheduling, but mostly all you're going to see is unconditionally scheduling. And then when you get down here, that's what I'm talking about. Call this sub, no conditions. Call this sub, no conditions. Call this sub, no conditions. It'll just go through. And what is in here? B2's lights. Where's B2 lights? It's right here. What's on B2 lights? Let's look into it. Here's ladder logic. Well, it looks like it's doing some timers and pulsing some timers and probably cascading some timers and turning on some lights and cascading them, pilot and beacon light logic. That's where it is. And it's just going to run this and it's going to blink these lights. And so it's going to get complicated with how everything is scheduled, especially if you have a big program trying to figure it out. Okay. And that's kind of what this lab is going to go in. I really recommend you read the lab and get an idea of it. One shot. We talked about a one shot. What a one shot rise and one shot fall into one shot is it is an instruction that you'll put in a rung and it will come high, let's say, and then it will execute the code in that rung once on the scan, and then it has to then go false again. The one shot will go false in order for any ladder, any logic on that ladder to occur again. Okay, and so you'll see one shots out there a lot. And one shot makes the rung true for one scan when the input rises and will not allow the rung to be true again until it goes false. And you're like, I don't understand why I would need that. I know, but we're going to get into a lot of complicated programs and stuff's going to be like, man, why is that resetting? I didn't reset that, or why is that light on? I did, that should have been done. And you'll start putting one shots in there to hold those conditions to when you want that stuff to actually occur. Okay. And once again, here's a little video that you can take a look at this on the D2L and see how one shot works. Toggle bit. That's where did everybody see how I showed you how to toggle a bit? You can just kind of turn it off and on to try and get stuff to work. It is not a force. All right. It is not a force. Okay. But sometimes you want to toggle something, you can toggle it and see what's going on, right? Not a force. Okay. This is quiz and lab. The main thing I was hoping you were going to get was some of the wiring on the safety relays, some of the wiring on the switch. If you get there earlier before me and you start working, you can always program as much as you can or ask Sean to get the switches out. I'll be in there on Monday, so I'll try and pull the switches out so they'll be on the bin on the front there if you want to take a look at it. Things like that. So that's what I got. You have a quiz. So what the quiz is multiple guess, and then you have to do, that's why I gave you that extra safety relay thing. You can do it on that. When you get done with that, you can take a picture of it and then email it to me. And then I will grade that at that point. So when you take the quiz, you're probably going to because that's worth points, and I haven't graded that yet. So, but I'll get it going. All right, that's a lot, I know. And so far, so good with you guys. You're hanging in there, and you're going to learn a lot this week, I think. But prepare yourselves by reading stuff. What time do I get? Probably depends on the traffic too. Definitely by like 4:30 I'm there. Because what time did you say you wanted to get there? Jeff, you could probably show up at 4 if you wanted to, or get there a little bit early, as long as there's somebody in the lab and you just want to start the programming part of it. And you're not going to hook anything up. Start getting into it. Get there. Yeah, get there at 4, and then I'll be there shortly thereafter. Is school open tomorrow? Does anybody know? You might have to call the help desk and find out because of the, I know you guys missed that today. That's what I was saying. You didn't get a chance to get in there today. But find out. It might be open, but tomorrow or tonight is super cold. But call the help desk and see what it is. 'Cause I don't know. Sorry, I didn't check on that, guys. All right, what else? What other questions you got? Yeah. Remember that those lights are DC, so keep the AC away from them when you guys start working on those safety relays. All right, anything else? You have a quiz that's open? I'll stay on if you have any questions, or go for it. Otherwise, stay warm and have a good weekend. But I'm here for questions or whatever. Winright Robotics out of Texas did it. I wasn't totally happy with them. I wanted somebody locally to do it, but we put it out for bid and nobody bid on it. So I was a little irritated, and I'm not happy. They use a phase manager. It's a really complicated scheduling process, which is okay. If you take, I know you're not taking PLC 3, but we go do a lot of scheduling with the phase manager and state managers and state machines and stuff like that. So you'll see that's even more complicated. Yeah, I wish I got a couple of companies that probably should have did it. Eckhart probably should have bid on it. I don't know, whatever. I was hired to facilitate it, but it was after it was already in the works. So they're like, "Here, Sean," and I'm like, "Who's doing it?" And they're like, "Winright from Texas." I'm like, "Okay, whatever, man." Got it dumped on my lap. Yep. Have a good weekend. Numbers done.